All right, hello AP Statistics students. We're going to be looking at a couple examples of some more sophisticated probability devices, methods, tools, if you will, for solving simple probability problems. So the first one was kind of alluded to in that little clip from the old video of Against All Odds with Percy Diaconis and his introduction on randomness and a little more discussion about probability. Right at the end, we left off, we were thinking about flipping a coin, right? So I wanted to use a new tool to figure out the probability of at least one tails when you flip a coin twice. So folks, so far, how would we attempt to do that? We already have one tool we could do that with.
Minus the probability of not getting a tails.
We'd use 1 minus the probability of not getting a tails. In other words, what's the name for that tool so we know where to find it in our belt and don't have to go searching around in the bottom? The complement. So that's like the complement tool. I'm going to show you how to do that with a tree diagram, probably the most important tool we'll be using this year. We're not going to really use that one in this assignment too much, but I just want to float it in there so you have an example and are exposed today. So if we want to diagram two flips of a coin with a tree, we're going to start by saying how many possible outcomes there are for each flip. So for a coin, of course, you either get heads or you get tails. That's the first flip. Then, after that, different stuff could happen. You're going to flip it one more time in this case. If you get heads, you still could get heads. Well, I'll be consistent. If you get heads or tails on the second flip, likewise here, you could get heads or tails. So that's the second flip. So this helps you diagram the sample space that they were talking about in the video very nicely. You can just multiply along the branches to find the actual probabilities, and then you can see all the different possible outcomes. This is, of course, a very simple scenario. Our tree doesn't have very many branches. But this idea of a tree is fundamentally important in this class and in future mathematics. In fact, it was the main thing worth more points than anything else on last year's AP exam. All the people who solved the last problem correctly told me they used a tree to do it. So pretty important stuff recently as well. So what outcome would we get here? First, let's name it, then we'll calculate it. Heads, heads. What outcome do we get here?
Tails.
Heads, tails. What outcome do we get here? Tails, heads. Notice a tree diagram also provides you the opportunity to list your outcome in order, which is kind of nice in some instances. In this case, it's pretty simple. It doesn't matter. Okay, so how do you figure out the actual chances of each one of these specified outcomes, heads, heads, and so forth? Well, what's the chance of getting a heads when you flip a coin? If it's a fair coin, unlike Mr. Diaconis' coin, then it's 50-50. So it's 50-50 here too, right? So if that's 50-50, then this is 1/2. And these are pretty much all 1/2. The nice thing about a tree diagram is if something changes, for instance, if you already don't put some cards back in the deck, or you don't put some M&Ms back like we were discussing last week, you can just adjust these probabilities on the second branch and you can go forward and still make your calculation. So we'll be doing lots of problems like that. But in this case, we get what? What's the probability of getting heads, heads? 1/4, because you multiply along the branches. 1/4 here. This is a pretty boring and easy problem. So how does this allow you to answer the original question, the probability of at least one tails, and not have to think about the complement? Well, you know all the specific outcomes. It's more clever, and I would argue more simple, to go 1 minus that one outcome to the whatever power, but here you could just see all the outcomes. At least one tails. Does this count? No. Does this count? Yes. Does this count? Yes. Does this count? Yes, because all three of those outcomes had at least one tail. So what's the answer? 3/4. So tree diagrams are really nice for when you have one event following another event, possibly following another and another event, especially where you have this issue of replacement. So we'll look at that tomorrow. What I want to look at today is not events that are independent, dependent, but events that are disjoint / not disjoint. Those kind of situations in probability, a nice simple diagram you can use, a nice tool is to use a Venn diagram. So the one at the top of your assignment, probability number 2, is a great example of this. What two events are we considering in that problem? Can you guys describe them for me? And let's give them a letter name. Pool, so should we call that event P? P is like probability though, you know, I don't really like that very much. Maybe, what's another name for pool? We'll say SW. Okay. You could be as elaborate with these descriptions or as inelaborate as you like. I'd be more elaborate. It's going to help you with your language. That's where you guys suffer the most, what I've found. So, swimming pool or not. The other event, something totally separate, or maybe not separate, but what was it? Garage. So it's natural to say G. So you could be a little more elaborate, like house has a garage. So, the most important thing when you're considering two events in combination like this is, based on the information you guys were given in that problem, do they overlap or are they disjoint? They do overlap. How do you know they overlap? They told you something. That some of the houses have both features, a pool and a garage. So we know there's some overlap. So when we draw these events in our Venn diagram universe, we should, of course, have some overlap. How much you scale that is up to you. The scale really doesn't matter. It's up to you. So we eventually have some problems we want to solve in regard to this problem. So how do we start labeling things? What did they say? They said swimming pool was how much? 21%. They said garage was, how many houses had a garage? 64%. Remember, we're just talking about one small community or something, right? We won't extend our results beyond that, but whatever, we won't worry about that too much today. And they told us one more number, right?
17.
Both was 17%. So how do you start labeling your diagram? Well, we said SW, so I'm going to say swimming pool. We'll call this event garage. So, likely, if you're not thinking, you might do this. Right? There's the overlap, the both. There's the garage. There's the swimming pool. Why is that wrong, Katie?
It should be 0.4 where it's 0.21 because it's 0.21 in the entire circle. So you need to count what's in the in-between circle.
If I do it like this, then the entire circle has 21 plus 17%. That says 38% of people have a swimming pool. Was that what they said? That says that, whatever, 90 whatever percent of this has a garage. Was that what they said, according to the survey that they conducted? The observational study or whatever it was? No. So, some problems you've got, and if this is true of a lot of Venn diagrammy problems, if you've got an and, it's always best to start with the middle. Start with the overlap. That's a note I would take down for sure. If it's a Venn diagram situation, if you can, I'd always start with the overlap. I will give you some situations on future probability assignments which will be a little bit tougher than this. They might not give you the overlap to begin with, and you're going to have to think about what overlaps with what, be a little bit creative. But if you have the overlap, start with it. You can see then, Katie said this circle wasn't 21%, it was how much? She said it was 4%, because 4 plus 17 equals 21. Now that's correct. This isn't 64%, it's what? What does that come out to? Help me, I don't have a calculator. You guys have a calculator, don't you? Okay, minus 20 is 44 plus 3. 47.
Okay, I did the math on the 0.21 one. My brain was fried.
Okay, so I don't know what questions they're going to ask me yet. Notice, I'm just filling out the diagram first. That's a good reflex for you guys to have, especially if it's a simple diagram. So that's the strategy I'd pursue, at least through the next couple assignments. So what other number do I need to fill out still? What other number is incomplete?
Square.
The houses that don't have either.
Out here, the houses that have nothing. Those sad individuals without a pool or swimming or garage, right? I don't know how you get along without a garage. So how do you figure out what is out here? 100% minus all those numbers. So what is 100 minus 47 minus 21? I don't know. Help me out.
32.
32%. I like to write these as decimals, not percentages, just because it's easier for me to stick them on the Venn diagram. That's up to you, of course, right? Okay. So what specifically were we asked to find? Probability of what?
Pool or.
So I'm going to say pool or garage, using my notation that I developed, right? Pool or garage. So what do you guys think for that? I think your diagram says it all. Does the 4% count? Yeah. Does the 17% count? Yeah. Does the 47% count? Yeah, because all those people have one or the other or both, or can include both, of course, right? So what do we add those up to? Isn't that going to be
8.
going to be the opposite of this? So that's going to be 68%. Is that right?
Yes.
Okay. They also asked us for the probability of what?
Neither pool nor garage.
So I'm going to put neither swimming pool nor garage. That's how I wrote it out. It doesn't matter how you write it out. It matters that you get the right answer. But I'm going to be looking for you struggling or not struggling, but having some description in here. Okay? If you're not, that's probably part of your problem. Why you mess them up? Neither swimming pool nor garage. What's the answer?
32%.
That's the 32%. And then what did they say? There's one other one, wasn't there?
Pool but no garage.
Probability of a pool. I'm going to say that intersected with or and no garage. How can I write no garage using symbols we've learned? I could go bar or I could say complement. So there's a real specific notation. You don't have to use it, but you might need it. It might come up on a multiple choice question or something at some point, right? So probability of swimming pool, but no or and no garage is which number up here? I think it's just one of our numbers.
4.
Those have a swimming pool. Those have both, so it's just those. It's just the 4%. Okay. So there's an example of a 2-event Venn diagram. Let's upgrade now and do a 3-event Venn diagram. You can do this in your notes or just on a scratch paper somewhere, or put it on that ESP thing, I don't care. So we'll come back and do that next.
Hi, Todd.
Okay, so here's a 3-event example. So we've got 100 students who are asked about their participation in some sports. I'm guessing this was not an exhaustive participation, so it must have been just like one season or something like that. Because it looks like, what are the 3 different options they were allowed to choose? Cross country, track, and lacrosse, where they participated in those sports. So this is all like outdoorsy sports, I guess. I don't know. Anyway, so those are the 3 events. So I have 3 events, so I'll label them very uniquely as L, CC, and T. I think you got what those mean. So if we were to follow my advice from the previous Venn diagram probability problem, where would we start? From the very center, right? And this is regardless of whether like maybe just 2 of these overlapped. You might have a problem where just 2 of them overlap and then one is disjoint to that pair. It's all kinds of possible combinations here. But you know, my assignments are going to build you up one step at a time. So, some of them aren't my assignments. Thanks, Ms. Dobson. So, what should I start with? What number?
0.2.
2, which we could call 0.02 since it's out of 100. But let's just count. How about that? So we'll just say 2. I'll put that way in the middle. Where should I go from there?
To the 0.3. 0.03.
I don't see a 3 on there.
That's the 5 minus the
Do you guys see it? So we took care of this. Then if we look at this one and go, 5 people played lacrosse and cross country. So lacrosse and cross country, that's this entire overlap, this entire intersection, if you want to say it properly. So if that's 5, then this must be 3, like Katie's saying. Okay, we took care of that. I like to check these off, especially on a 3-event problem or 4-event problem. Oh my gosh, it'll start to get tricky. Anyway, but we don't have to deal with those. So. 5 people also played lacrosse and track. So lacrosse and track, this whole intersection is 5. So that's also 3. 10 people played track and cross country. So the intersection between track and cross country, this intersection should be 10, so this must be 8. Took care of that. There were 25 people who played track total. So how many people played just track but not one of the other 2? 12. How'd they come up with that? They went 25 minus 10 and 3 is 13. You get 12. And then likewise you can fill these ones in, right? So cross country, total of 15 people played. Looks like we've already got 10 and 3 of them consumed. So there's only 2 people who just did cross country. And likewise for lacrosse, we've already consumed 5 and 3, 8, so there's 12 out of the 20 left. So we still need to fill in one other number on our Venn diagram, and that's what remains in the universe of athletic participation at this school, for this situation at least, this season. So what is that going to be? We could just take all of these and add them up and take it out of the whole, which is 100 people, right? Usually you're going to have percentages in here, so it's weird that I counted it. The only reason I did that is because we've got exactly 100 people, and I thought it made it nice and easy for this example. So what is it? Can you guys tell me?
40.
Did it add up to 40?
Well, I got 42.
This adds up to 60?
I think so.
Okay, I'll trust Gabe. So if that adds up to 60, do we have confirmation?
I got 42, but I'm adding up again.
I don't know.
I'm not a calculator.
It adds up to 60. Yeah, so that is cross country track. It's 60. Like 60.
Yeah, you could do it that way too. Very nice. You could just add those up. I'm going to play it safe though and say 24 plus 6 plus 10 plus 2. So I get 30 plus 12. I got 42. So that means there's 60,
No, 58.
58 people left over. So now we should be able to answer pretty much any question they ask us, no matter how complicated. We could answer how many played cross country only. 2. So that could be 2 out of 100 for 2% if we wanted to turn it into that. How many played cross country and track?
8.
You could even just go back over here to your list and study your diagram on that one, right? Cross country and track was 10 out of 100. If you're looking at this, you got to look at this overlap between cross country and track, which is this whole thing, which is 10, right?
What if they said just cross country and track?
If they said just cross country and track, that would be
Wouldn't it be 8?
just cross country and track would be 8. Yeah, you're right. Very nice. What about the probability of cross country? What's that bar on top mean?
Not.
Another way to say not cross country. So not cross country is. So I thought before we left this final 3 event probability example that we'd look at a couple more interesting questions. So we've already figured out all the different probabilities of individual events and their combinations. So I thought we'd look at first the those last couple that I left off a second ago. So I think they were the probability of cross-country complement. So that's just everyone not in cross-country. So if cross-country is 5 plus 10 being 15 people participated in that, complement would of course be 85 out of the sample space. So in this case, 85%. The final thing said the probability of none. You can see that was already done in our setup. So that would be 58%. So let's look at these. I think a couple of them are a little more interesting. So what's the probability of playing lacrosse or playing track? So that's one or the other or both or any combination thereof. So I think we need to start looking at anything that's in the track circle and anything that's in the lacrosse circle and just make sure we don't count anything twice. So let's add those up. So it looks like we're going to have 12 and this 12 and that 3 and that 3, so I'll say 6. And that 2 and that 8, because that 8 is in the track circle. So it's going to be 10. So that looks like it's going to be 24 plus 16 is 40 out of 100, or 40% for this problem. So now let's look at the probability of playing track at the school or cross country, but not lacrosse. So the condition gets a little bit more picky in this case. So track or cross country would be anything in the T bubble or the cross country bubble, but you want to make sure that you're not playing lacrosse. So in that case, I might make big X through the parts that don't matter. So for instance, this 3 wouldn't count, this 2 wouldn't count, and this 3 wouldn't count because those are all part of the lacrosse bubble. So it looks like all I'm left with are the 2 here, the 8 here, and the 12 here. So if I add those up, we're going to get 12 and 8 is 20, plus 2 is 22 out of 100. So in this case, 22%. But of course, usually your sample space isn't going to be an even 100 students like this one. Okay, so I think that was a much better example of the kind of caliber of questions we need to be prepared for. Let's see, how about the probability of track or having played no sport at all, nothing? So track or nothing will be anything in the T bubble plus this outside region in our universe. So I think that guy's going to be 58, plus the track is going to be 20, plus 5 is 25. So that's almost 60 plus 25, which would be 85. So it's just going to be 83% in that case. Okay, so I don't know if these will come up in probability homework number 2, but since we have the opportunity, I thought we'd start to look at our first, what are called conditional probabilities. Conditional probabilities will have a special symbol. A good clue to a conditional probability for now is this word called given. So, the first one is the probability of playing lacrosse given that you've already played track. So you have to be a track player in order to make this work. So in other words, that's the sample space. We've changed the sample space from 100 students and narrowed it down to just those students who play track. They have to play track before they can be considered. So how many track players were there overall in the T bubble? There were 20 plus 5 is 25. So in that bubble there were 25, so now we're just interested in the lacrosse players out of that sample space, so a narrower sample space. So lacrosse players out of that 25, those players played lacrosse and those players played lacrosse. So I think it's just 5 out of 25, which in this case reduces to 1/5, and I know that that's actually 20%. So there's your first example of a given probability or a conditional probability. Really important for our class and for any kind of probability, pretty much. So let's look at another given probability before we leave off with that. What's the probability of someone playing track given that the person plays more than one sport? So if they play more than one sport, I'm going to finally mess up my Venn diagram here, then our sample space is confined to people who played 2 sports or 3 sports. So the only things that would count are these numbers that I'm going to circle. Those are the only people who played more than one sport. So if we add those up, we'll get our narrowed sample space in this case. So that's going to be what? 10 and 6. So I think that's 16 players. Only 16 players played more than one sport. So what's the probability someone played track given that they were in those 16? So that of course is just the track numbers. This person played track and so did those people. Those 2 played all 3, that means they played track, and those 8 played these 2, which means they played track. So that would be 10 out of 16, which I could of course reduce to 5/8, which is 62.5%, I believe, if you put it in your calculator. Okay, so there's another example of using a Venn diagram as a probability tool. So we've introduced just barely tree diagrams. We'll look at that more this week. Now we have Venn diagrams in addition to our basic complement and add/multiply strategies. I'll see you next time.